Now we're going to move on to fluid flow and wave equations. First, we're asked to derive the continuity equation, which I wrote right there, where rho is the density depending on position r and time t, and v is the velocity. Okay, so we're asked to find, or to show that the partial of rho density with respect to time plus the divergence of rho times v is 0. Okay, that's the continuity equation. And it actually comes from the law of conservation of mass. It says that the rate of increase of mass should equal the rate at which mass is flowing in through the boundary of a region omega. Okay, so it actually makes perfect sense. Let me write it out in math. So, sorry. Let me just write out the triple integrals. So omega is some three-dimensional region, and rho is density, right? So if we integrate rho on the region omega, we get mass. And if we differentiate this whole thing, then this is basically the rate of increase in the mass. Okay? So this is rate of increase of the mass in the region omega. And what should it equal by the law of conservation? It should equal the change, okay, the rate at which mass is flowing into omega. But it flows in through the boundary, okay? So just imagine the surface area, okay? Just imagine omega as a box, and we are only focusing on the surface. We have fluid flowing in through the surface. Okay, so this equals the rate at which mass flows in through the boundary. And in using notation, we can write this as the double integral over the boundary of the mass. So we're integrating over rho, but then we have to multiply this by v because it's mass flow into. And because the normal vector n usually points out, we're going to write negative right here to indicate that we're actually flowing in. Okay. But what is this? What is this? This is just by the divergence theorem. What's the divergence theorem? It states that the double integral over the boundary of f dot ds is the triple integral over the region of the divergence. Right? So using the divergence theorem, this is equal to the triple integral of the divergence of rho v. Right? And because these two are equal, what we started with was right here in the beginning, and here's what we ended up with. They're equal. And so I'm going to add this result to both sides of the equation, and I'm going to get, actually I'm going to write that as partial, because rho, the density, not only depends on time, but it also depends on the location. Okay, so it's all of this is equal to 0. But because this whole integral is equal to 0, we can conclude that everything inside was actually 0, which was what we wanted to prove here. Okay, so A is done.